good afternoon, good evening, or good morning, depending on where you are and what you're doing. This is our first day in Calculus, Unit 5 today. And what we're going to be doing today, guys, is we're going to be looking at maximum minimum problems. So if you remember back to Pre-Cal 30 problems in grade 12 math, where you had to, and maybe grade 11 even, I think it started in grade 11, where you had to maximize and minimize quadratic equations with area, minimize and maximize numbers. That's what we're going to start doing. And what we use is derivatives. Because what derivatives actually tell us, is, if we're talking about curves, is the rate of change of something. Okay? So that's what we're going to be looking at here today. And we're going to be looking at a couple of different examples of each. Today we're only going to do two basic type of examples. This will probably take us 2 or 3 parts to do. So it'll be maybe 2-parter or a 3-parter section in this Unit 5 area. So first of all, let's set up our board here. Let's outline what we're going to do today. So this is Unit 5, and this is day 1. Okay, and that's the maximum and minimum stuff. Probably the most important part of calculus. This will be our part of calculus where we're doing a lot of word problems and solving practical situations. Okay, so this is basically applications with derivatives that we're going to be doing. And today we're going to be doing a couple of things. We're going to look at maximum and minimum problems. Okay, and under maximum and minimum problems, I think we're going to do an area example today. And let's see here, my background. We'll get into area. Yeah, we'll do the area problems first. So I think we'll do 2 different kinds of area problems, area perimeter problems. Okay. So we're going to do max and min problems, and we're going to do examples of max area and one of min area. So we'll do 2 today. So this is our first part that we're going to do, and that's as far as we're going to get today in calculus. So it'll probably take us a good 30 minutes to get through this. I don't even think I'll give you any practice today. I'll save that for the third day. First day we'll probably do max and min problems. Second day we'll probably do a couple more different kinds of examples. And the third day we'll do some practice with it. Okay, so the first one we're going to look at is we're going to look at a max area problem. That uses perimeter and area. Okay, so like a fencing problem. Okay, so let's set it up. So a farmer has 1,200 feet of fence wire. Okay. Plans on making a pen with the backside being his barn. Okay. Wall. Find the dimensions of the pen to maximize the area. Tomorrow we'll do another similar example like this that'll deal with cost, but not today. We'll just do the basic area type one here. So first thing we have to do is do a little sketch. So I'm going to take out my marker here and we'll do a little sketch. So if this is the barn wall here, let's change to marker here first. Okay, if this is my barn here, okay, and I'm going to have my fencing material come out so that I have maximum area. I need it to be some width and some length here. This will also be a width. Okay, so what we have is we have two equations to look at here. We have an equation for the area. We have an equation for the fencing perimeter. Okay, so first thing we do is we write the perimeter equation. So we know that according to perimeter, that 1,200 meters, or feet, pardon me, of fence is equal to this plus this plus this. So if we reduce that down, we've got 2W plus L. So that is the perimeter of the fence, not including the barn, because the barn is not part of what he has for fence. It's just the wall. We're assuming the barn's long enough to include it. So, but we want to maximize the area. So his area equation is completely different. Okay, so the area, this is the perimeter equation right there. So the area equation is equal to width times length. Okay, and what we want to do here is we want to maximize the area. So we're going to have to work with the area equation. So we're going to have to use this perimeter equation to solve for L or solve for W. And then, so we don't want two variables in the area equation. We've got three variables. We've got area, we've got width, and we got length. We want to remove the width or length from this equation. So we're going to use the perimeter type equation here, and we're going to solve for L. So first step is use one equation, or the perimeter equation, to solve for W or L. One of the variables. Okay, so we've got W and L in there. So I'm going to solve for L because it's a little easier. So I'm going to get 1,200 minus 2 W's equals L if I subtract 2W from both sides. Okay. Second step is now to rewrite the area formula in terms of one variable. Is step 2. Because we're maximizing area, so we want it in one variable. So you want one variable. So we rewrite the area formula in terms of one variable. Now, some people are going to ask me, would it make a difference if I solve for W? No, it wouldn't. You would get a different equation, but it would work out that you would solve for W in the diagram, and that would be fine instead of solving for L the other way, because they may be different, right? But you'll get the same dimensions no matter which one you choose. So if I do that, we've got area equals length times width. Put in the W, so area equals length, which is 1,200 minus 2 W's times a W. Okay, so I'm going to simplify that using area using distribution equals 1,200 W's minus 2W squared. Okay, Now we want maximum area. So the third step is to take the derivative of the area. The derivative, if we take the derivative to get that maximum, there's either going to be a max or min when the derivative is equal to 0, right? The critical point. If you remember critical points from the last unit, when you take a derivative of that, you end up getting where it's 0 and equal it to 0, you end up getting a max value or a min value. So we're going to end up getting our maximum value by getting the derivative. So the derivative in step 3 tells us where the critical point for max or min could be. Use the derivative of A and set it to 0. To find a max min point. Okay, and we called these last time. Why am I putting brackets there? I don't know. You don't need brackets there. That's stupid. To find a max min point. Okay, we called these crit points. Okay, it's a critical point, like we learned in the first and second derivative test for what we have. So, okay, let's do that now. Let's solve for our maximum area. So we're going to take A prime with respect to W in this case. So we're actually taking dW dA, if we write it like this. Okay, that's the derivative we're doing, or A prime is the way I like to write it. Okay, the derivative of this would be, derivative of that is 1200 minus 4W. So now if we set the derivative to 0 and solve it, we will have a critical point where W is equal to a certain value. So set this to 0. And this critical point, we can move this over to the other side. So we are ending up with W is equal to 300. We divide both by -4. Okay, that only tells us what the width is, but we need the length. So then we have to find L. Okay, we know that L is equal to 1200 minus 2 W's, right? So 1200 minus 2 times 300. So this is going to give us 600 for L. So then we know that the dimensions of our pen is a length of 600 feet and a width of 300 feet. Means therefore, the dimensions are 600 feet by 300 feet. Okay, so the max area then, if they ask you what the max area was, that would equal 600 times 300 would be 18, or well, I guess it's 4 zeros. So 180,000 square feet. Lots of area there. Okay, so that's a typical area max and minimum. Now tomorrow we're going to do a slight variance on this. We're going to throw in a cost one. You know, we're going to say like he uses 2 different types of fencing material and change our equation and do things like that. But we'll save that one for tomorrow. Okay, the other type of question that we're going to do in this A part is maximum minimum stuff. Is we're going to do a min one. Okay, let's do like a minimum area. So a lot of times they'll give you a poster problem or a picture problem where you're doing, remember where you have to frame a picture or frame type text of a poster or something like that. So let's do one like that. Okay, so that one was about 15 minutes. So again, I want to keep these to about 30 to 35 minutes because we do have a few schools that have 45-minute periods rather than the hour. So, okay, so that's just summarize, draw your diagram. Okay, write your perimeter and area formulas. Okay, solve using the perimeter formula, one variable into the other. Plug it into the maximum, minimum, what you're trying to maximize or minimize. Okay, if they gave you the area and then wanted you to maximize or minimize the perimeter, you'd have to do it the other way around. Okay, and we'll maybe do an example like that as well. And then use the derivative of area to get a max min point or a critical point to solve for your area. And that's basically how you do that one. Okay, so let's do another example on the second page. Let's do an example where we're going to use, let's see what I got in my background here. Let's see here. Yeah, this one's. Well, let's do another one like this. Let's do see if you can do one like this. Okay, let's say what we have, let's do the diagram one. So let's say we have a wall that goes like this. Okay. This is wall, and we're going to put a pen this time that goes like this. Okay, comes off that wall, goes out here, and comes back in. Okay, so let's label this up. Let's say that, well, let's type the question above it here or below it. It doesn't really matter where, but I'll type it here. Okay, we have 170 feet of planks. To make a pen. Okay. Diagram below. And use the diagram below. To find the max area and dimensions. Okay, so let's say on this type of example, let's say that this is 10 feet out. Let's label it up. So let's call this is 10 feet here. We have 170 feet of planking. That's the red stuff. Okay, and this is our wall. Okay, and this is 10 feet here. So then if we label this up, this is W, this is L, this little piece would be W minus the 10 feet. Okay. So I'm going to give you a chance to do it so you will maximize that area. Okay, so write the perimeter equation, solve for L or W, plug it into the area equation, do the derivative equal to 0, solve the variables, see what you get. So pause the video there and give that a whirl. And then when you unpause it, I'll work it out. Okay, so if you've unpaused it, let's do the perimeter first. So we've got 170 feet. That's going to be W plus L plus W plus L plus W minus 10. Okay, so if I work that out, we got 170 equals 2W plus L minus 10. We got to bring the 10 over. 180 equals 2W plus L. So if I want to solve for L, L equals 180 minus 2W. Okay, so that's our starting point. Okay, and then if we take A is going to be equal to length times width. That's what we want to maximize, the area. So then if I plug in the L value here, A is equal to 180 minus 2W times W. The area will equal 180W minus 2W squared. Okay, so now we're into taking our derivative. So dW dA, or A prime if you like, it's going to be 180 subtract 4W. Okay, very similar to what we did last time. Okay, solving for it, we got to bring the 180 over. So if we bring 180 over, so divide both sides by -4. -4 into this would be 45 equals W. So this side here is 45. This would be 35. Okay, so our dimensions of the pen would be 45 by whatever L is. L equals 180 minus 2 times 45 equals 180 minus 90, which equals 90. So it'll be 90 feet is the dimensions. Okay, and the area would be 45 times 90, which is whatever that is. That's right, 4,050 square feet. Okay, so that's an example like that. Okay, we did 2 area examples. So the other one is a minimum area one, or a photo one, which is, I was kind of getting into that before I decided to make you do one of these ones. So let me check my time here. Okay, that's 22, so we'll have enough time to do one more. Let's do an example of printed page one. I like those ones where you leave a margin. So a poster problem will do. Okay, this time we'll use wording to do this one. So this is our last example for today, in this period anyway. Okay, so we're going to do a poster. So let's set this up. So we want to print a poster with 90 square inches. Of printed material. With a margin on the top and bottom of 2 inches. Okay. And period, side margins will be 1.5 inches. Find the dimensions of the page to use the least amount of paper. So we're minimizing the area in this case again. Okay, so let's draw our picture so we see what's going on here. So I'm going to have the printed material inside the other one. So this is going to be, let's draw rectangles here. Okay, so we'll use this here, rectangle. So, okay, there's our printed page. Inside that, we're going to have our printed material. Okay, so that's what it looks like. Sorry, guys. Okay, so according to this, there's 90 inches of square inches of printed material. So this material in the middle here is 90 square inches. Okay, well, we can say that we can do this one of two ways. We can put the area, say X and Y for horizontal and vertical. So if we call this dimension X, the horizontal, and this one Y, okay, so there is 1.5 inches here and 1.5 inches here. There's 3 inches here, or sorry, 2 inches here and 2 inches here. So this dimension of this outside paper is going to be Y plus 4. This dimension is going to be X plus 3. So your minimum area that's going to print that out is going to be this stuff here. So in this case, we're not using perimeter, we're using two areas. So we got to do the inside area. Okay, the inside area is X times Y equals 90. Okay, so that's not what we're trying to maximize or minimize. The outside area is what we're trying, the paper area. Is equal to X plus 3 times Y plus 4. Okay, and we'll just call that the outside area A. This is what we're trying to minimize here. Okay, but we cannot do that. Now there's two ways we can do this. we have to eliminate an X or a Y. Well, there's actually 4 ways we can do it. But we have to eliminate the X or Y. So the first thing we should do is we take the inside area equation and solve for one of the variables. So solve for the variable in the given equation that's there. Okay, so I'm going to solve for Y. So Y is going to be 90 divided by X. Okay, so I'm going to plug in and remove the Y in the area equation that is going to be on the outside page now. So I'm going to take this, and I'm going to take this paper area equation, plug in the Y here, and that's going to give us an opportunity to eliminate the Y and only have X there. Okay, so that's step 2. Okay, so plug this in. This was step 1. So plug in Y. Okay, so let's do that. So the area equation was equal to X plus 3 times Y plus 4. So Y is going to be this 90 over X plus 4. Okay, so now we have to do foiling to simplify our area equation for the paper. So we simplify this paper equation now. So X times 90 over X. Okay, you're like, okay, well, I don't know how to do that. Yes, you do. That's just going to be canceling out the X's, right? So it's 90. X times 90 over X This is like 90x over x, which would be 90. Okay, and then we go x times 4, which would be 4x. 3 times 90 is 270 over x. And 3 times 4 is 12. Okay, so we have to do some simplification here. Okay, so 12 and 90 can be added, and then we can rewrite this as a negative exponent. So I'm going to put the 4x first. Then I'm going to put plus 270 x to the power of negative 1 because it's on the bottom, bring it up to the top. And 90 plus 12 is 102. Okay, so there we have area in terms of x. Now we want to take dx dA. So we want to take dx dA, the derivative of a with respect to x. So do it. Step 3 is take the derivative. Okay, so our derivative is 4. Okay, you have to be careful with this one. When you take the derivative of this one, okay, we got to take the negative out front, negative 270 x to the power of negative 2, right? And derivative of that is just 0. Okay, and then we have to take the derivative, a prime I should put in there. Now we have to set the derivative to 0. Okay, now this is where people get all messed up and can't solve it. So now, in order to help us to solve this, okay, what we're going to do is we're going to put the x squared back on the bottom. And we're going to move the 4 over. Okay, so I'm going to move the 4 over to make negative 4. And I'm going to write this as negative 270 over x squared. Okay, now we can solve it with cross multiplication. This is like negative 4 over 1, so cross multiply. Okay, so this is negative 4x squared equals negative 270. Okay, divide both sides by negative 4 to get your value for what x squared would be. Okay, so negative 4 into into negative 270, so this would be x squared is equal to 67.5. Okay, and then take the square root. Now you have 2 possible answers here. Plus or minus. Okay, so what's that? Square root of 67.5. Uh, 3 root 30 over 2 or 8.2. Doesn't make sense if it's negative, right? You can't have a negative dimension in terms of length and width. So then therefore x equals plus 8.2. Okay, and when we go back up here to find out what y is equal to 90 divided by x. So we can solve for y. Solve for y. So 90 divided by 8.2. Okay, so that is going to be, what is that going to be? 90 divided by 8.2, 11.0, approximately. Okay, but that's not our dimensions. That's x and y. Let's look at a diagram. The paper is x plus 3 and y plus 4. So your final dimensions is solve for the dimensions. Okay, so solving the paper dimensions would be x plus 3 equals the width. So that x was 8.2 plus 3. That would be 11.2. inches. And y plus 4. So this would be 11.0 plus 4, which equals 15.0 inches. So our dimensions would be 11.2 inches by 15.0 inches. Oh, I'm just going to use the 2 knots there for inches. You don't need to write the word inches if you don't want to. So there's our dimensions of that page. Okay, so that would be whatever the area would be, approximately 168 square inches. Okay, so we'll stop there today. That gives us, we're getting right into that. We're at 35 minutes there, so we'll stop at that point. Next day we'll do the second part, and then the third day we'll do some practices with the 3 or 4 different types of examples that I show you. Okay, so we'll see you next day.